In this video, we're going to do some vector space proofs with linear transformations. So I'm going to let M subscript 2 by 2, so all 2 by 2 matrices be a vector space. So I have a transformation from M2 by 2 to M2 by 2, which means we take a 2 by 2 matrix, we put it through a function, and then it becomes another 2 by 2 matrix. So I want to show as a linear transformation where our transformation function takes a matrix A, takes itself and adds its transpose. So we're going to let A be equal to ABCD. So I want to show it's a linear transformation, so there's two requirements. The first requirement is that if I have T and then I take A plus B, this is going to be the same thing as the transformation on A plus the transformation of B. And then the second part is if I take a transformation A and I multiply it by a scalar, so I have T of CA, this is just equal to the scalar times the transformation on A. So, to do this, let's take T of A plus B. So T of A plus B, well, now we just put A plus B into where all of our A's are, so this is going to be A plus B, and then it's going to be A plus B transpose. Okay, so we can simplify the transpose a bit, so we have A plus B, and then we remember that when we take the transpose of two added things, we just take the transpose of each and add them together. It's going to be A transpose plus B transpose. Now let's group our A's together. So we're going to have A plus A transpose plus B transpose. Oh, so this is just the transformation of A plus the transformation of B. Okay, so our first condition has been met. Our second condition, take a scalar, multiply by A, transform that. That's the same thing as taking the scalar, then multiplying the transformation. So T of C times A, well, this is just going to be C times A plus CA transpose. Okay, well, we just keep CA the same. We do the transpose, so we can factor out the C and then have A transpose. Then we can factor out the C from both of these, and we'll be left with A times A transpose. And this is just the same thing as T times the transformation of A, or C times the transformation of A. So we've proven that both conditions hold, therefore this is a linear transformation. So, was it even necessary to define this? No, doesn't matter. Okay, that's the first part. Second part, I'm going to let B be in the set of 2 by 2 matrices. So this is the vector space of 2 by 2 matrices, and B is going to equal B transpose. I want to find an A such that the transformation of A is equal to B. So just as a reminder, the transformation of A is equal to A plus A transpose. So essentially what I'm saying is I want the transformation of A to equal B. So this means that A plus A transpose has to equal B. But I'm also given the information that B is equal to B transpose. So, what if I had 1/2 B plus 1/2 B? Well, that's equal to B. Oh wait, but this has to be a transpose. So I can have 1/2 B, and luckily B is equal to B transpose, so I can have 1/2 B transpose, and that's equal to B. So, if I put in 1/2 B as our A, then I get B back. So, the A I've chosen is equal to 1/2 B. So that's how you find the B in the vector space of 2 by 2 matrices, such that the transformation on A gives you back B. So this is one of those things that might not be easy to see right away, but as soon as I see that B is equal to B transpose, I'm immediately thinking, okay, if I want to get B back, then I just have to add 1/2 B plus 1/2 B. And then I need to see if I can somehow get it to work in the equation. Okay, so luckily this one worked out nicely. I'm sure some of them are much harder, but I couldn't find any that were really that were a middle ground, somewhere between really easy and stupid hard. So it's hard to find those middle ones, but anyways, that's the video. If you have any questions, please leave them in the comments below, and I'll do my best to answer them.